Alright, now we're going to work on polynomial functions. So starting with number 1, I want to find the appropriate values for the relative minimum and maximums of this function. Now some of the stuff I'm going to do in my calculator, and it's because I can't do mins and maxes on my iPad calculator. You're just going to have to kind of listen and follow along. But this one we're going to have to plug into our calculator here. So we have x to the 4th minus 3x cubed plus 3x squared plus 5x minus 4. And when you graph it, you just have to try to get your window to look right. So if you do zoom 6 and you try to graph this, you always obviously hope everything fits, but if it doesn't, you're obviously going to have to make a few changes. Now this one, it does fit, but if you hit zoom 4, it does zoom it in a little bit, and you can it doesn't work too well. So here's the window I would use for this one. Okay, I'm going to go down a little bit. If you did zoom 4, you just can't see it all the way. So I want to go -6, and I should be able to see my entire graph. There we go. Okay, so here's what I'm looking at when I did my window from -5 to 5. And then I'm going from -6 to 5. So when you graph that, this is what your graph is going to be doing. It's going to come down, and it's probably hard to see here, but your graph has some complex roots in it. It's going to go through 0, -4, and it does a few little curves there. It's really hard to see. I'm maybe even exaggerating it just a little bit, but you know right now it has 2 zeros. Well, there's 2 other zeros hiding, and again you can probably see your graph kind of looks like it's kind of wiggling to the right a little bit. It's adding an extra little loop in there. Okay, it's just very subtle. So, but it only has one minimum, as you can tell. It only goes down once, and it doesn't really, have any other values. So we just have to find that one point. So that's all we're really doing. So we're going to go second calculate. We're going to find that minimum. And you're going to go second calculate, hit minimum, and then remember it's going to ask you for a left bound and a right bound, and then you just need to guess. And if you do that correctly, on this one we should get -0.45, 0.457, and our y value should be -5.329. And that's that point right here. Again, second calc minimum, and then do what it says. And that's all you gotta do for number 1. Just graph it and find that minimum and find it. Okay? And calculate it. So here we want the intervals of increase and decrease for the function from number 1. So using this point, you'll see it's going down up to that point, and then it's going to start going up. Even when it curves a little bit to the right, it doesn't start to go down. It just kind of curves, and then it's still increasing. So that whole period is going to be increasing. So we're going to have decreasing and increasing here, intervals. My decreasing intervals are -infinity to -0.457, and my increasing intervals are going to be from -0.457 to infinity. So you got your decreasing and your increasing intervals for number 2. Alright, number 3, we're just going to be doing just some basic evaluating functions. So this is one of those little things that got cut out based off of time, but we're going to talk about it here because it's Algebra 2 review. And it's just understanding when we're evaluating a piecewise graph, you need to look at the intervals for each piece of the function. So if I'm asking you, and actually I'll color coordinate this, sometimes it's easier that way. So if we're doing p of -5, for instance, notice p of -5, I'm going to color coordinate it, it's less than, the x value is less than -4. So that tells me I'm going to plug this in to that square root of -2x plus 15. So this is -2 times -5 plus 15, becomes the square root of 10 plus 15, so 25. So you end up with 5. So that's p of negative 5. If I ask for p of positive 5, now we're dealing with our, x is greater than 4, so I'm dealing with that quadratic function. So I'm going to go 2 times 5 squared minus 3 times 5 plus 1. So that's 25 times 2, so 50 minus 15 plus 1. So that's 35 plus 1, so 36. Once you know where to plug in, it's really not so bad. And the last one, p of 4, notice that is equal to 4. Notice if x equals 4, we're going to use that absolute value function. So I'm going to go absolute value of 3 times 4 is 12. Absolute value 12, well, that's 12. So there you go. That's evaluating piecewise. Not so bad. Just got to know where to plug in. Make sure you pay attention to those intervals. So moving on to number 4, identify domain. So again, the only issue we have in this case is this denominator. Two things that we can't have. We can't have our radical equal to 0, and we can't have it negative. So what we're going to do is take that input at 3 minus 4x, set it equal to 0. Let's figure out what that 0 is, and then we'll take that 0, put it on a number line, and test it. So this will be 3 equals 4x, and x is equal to, in this case, 3/4. So I'm going to take that number. Remember, x can't equal 3/4 in this case. Normally it can, but when it's in a denominator, it's not okay. All right, so I'm going to take my 3/4. I'm going to test that point out. I'm going to pick 0 and 1. Now, those are some pretty easy ones to pick. So remember, we're plugging in here. So when we plug in 0, we're going to have 3 minus 0, because 4 times 0 is 0. 3 minus 0 is 3, which is a positive number. Because remember, you fourth root, it's going to be ugly, but who cares? It's positive. So that one's going to be good. You plug in 1 right here. That's 3 minus 4 times 1 is negative 1. 3 minus 4 is negative 1, so that's going to be negative. So my domain is negative infinity. Now remember, we cannot touch 3/4. So our domain would look like that on a number line, so it's negative infinity to 3/4. And we don't touch it. And that's your domain for number 4. Moving on, evaluate. Now here, remember, all we're doing is we're doing that difference quotient. We're just doing slope. Now this is a line. So when you see that this is a line, this should actually make this problem super easy. The slope is negative 3/2. So please just write that and don't do all the work. There's number 5. Wow, that was quick. Okay. But on number 6, we got to do a little bit of work. For this one, we have to find f of x plus h before we solve this. So this is going to be 2x plus h quantity squared minus 1. That is f of x plus h. You take your x, you change it to x plus h. So that's going to be 2x plus h times x plus h. You got to FOIL that out, which is just distributive property. So this becomes 2, and then in parentheses we have x squared plus 2xh plus h squared minus 1, which is 2x squared plus 4xh plus 2h squared minus 1. This is the simplified version of f of x plus h. So I'm going to take that and subtract them and divide by h. So now we're going to do the difference quotient. Again, I'm just doing this. Here we go. So f of x plus h, that is 2x squared plus 4xh plus 2h squared minus 1 minus 2x squared minus 1 in parentheses over h. Now if you're doing this right, that h on bottom should end up canceling out. If it doesn't, you're done plain screwed up. So the 2x squareds, those go away. Notice we distribute that negative, so it's going to become a plus. So the negative ones are going to cancel. So you're left with 4xh plus 2h squared over h. Factor out a GCF of h. You get 4x plus 2h, which cancel, and there you go. Notice the h cancels. That usually is a good sign that you did it right. And that is number 6, difference quotient. Number 7, I'm going to take a graph. I'm going to find a bunch of stuff here. So this graph, we are going to start with the end behavior. Again, this just look at that leading term. It's in standard form. So I know that this graph is going to look like this. Okay, so I am going to start with my limit as x approaches infinity. So as I go to the right, what is my y value doing? Well, it's going down. So that's negative infinity. And as x goes to the left, I'm going up, so that's positive infinity. So that's my end behavior. Once we get that, we want to find our x-intercepts. So in order to do that, we have to factor this function. So I'm going to pull out, in this case, I'll pull out a negative x, just to make this now x squared minus 5x plus 4. So I'm doing that first. I'm just factoring this so I can find my x-intercepts. So I'm going to have negative x. This will be x and 4 and 1. Minus 4 minus 1 would give me negative 5. So I have x equals 0. I have x equals 4. And I have x equals 1 as my 3 x-intercepts. So your x-intercepts are 0, 1, and 4. Your y-intercept, well, since you notice I have an x-intercept at 0, I'm going to have a y-intercept at 0 as well, because it's going through the origin. But remember, in other words, all you have to do, if it's in standard form, it's the constant. Well, I don't have a constant here, so it's 0. So that's your y-intercept, and now we graph it. So I have my points at 0. I have a point at 1 and one at 4. So those are my 3 points. Remember your end behavior, it's going to start at the top and end up going down. So I'm going to start up here. I'm going to go through this first point, curve back up, and I'm going to curve back down. So there's your graph. So the only other thing I haven't labeled so far is the number of turning points. So in this case, we just want to see how many times does it change direction. So we have this point and this point. So it's going to change directions 2 times in this case. So we have, again, number of turning points is going to be 2. So that's all we have in that case. Alright, so that is number 7. Number 8. Come over here and we're going to graph this one as well. So I have first off my degrees. Since it's in factored form, remember we have to add our degrees up. So this would be an x to the 8th power polynomial. So it's going to be up and up. So number 8, my end behavior is infinity and infinity for both because it's always going to be going up. Alright, now your x-intercepts on this one, it's already in factored form, so I have, I'm going to have negative 1. Negative 1 is going to have a multiplicity of 5, which means it's going to flatten. It will still go through the point, but it's going to flatten. Next up, I have positive 1. This one's going to have a multiplicity of 2, so it's going to bounce. And the last point, that's 2x minus 9 equals 1. So if you take this, 2x minus 9 equals 0, not equals 1, it had a multiplicity of 1, sorry, which isn't a multiplicity, but whatever. So this is going to be 2x equals 9, and x is 9 halves, so 4.5 would probably be fine here. As I said, this one doesn't have a multiplicity. So those are your x-intercepts. Your y-intercept is basically just f of 0. So that's going to be 0 plus 1, so 1 to the 5th times. And we have 0 minus 1, so negative 1 squared. And then we have 2 times 0 minus 9, so negative 9. So this ends up being 1 times negative 9, and here you go. So there's your y-intercept. So the only thing I don't have is my turning points. We'll get that when we see our graph, but let's go ahead and put that on here. And I'm going to give myself space to do that -9. So I have -1 and 1 for my x-intercept, so make sure I get those labeled. So -1 and 1. I'll go out to 5 so I can get my other point. 2, 3, 4, and one more. I'll go out 5. So 4.5 is right there in the middle. So those are my x-intercepts. My y-intercept is at -9. I'll just kind of put it down here. That's fine. So 0, -9. And remember, I'm going up and up, so I better end up going up. So pay attention to your multiplicities here. My first one is a multiplicity of 5, so it's going to flatten. So I'm going to get there a little early. I'm going to get flat. And then it's going to go down. My next one's going to be at 1, but I got to go all the way down to -9 first. So it's going to go straight down. It's going to curve back up. And remember, this next point, when I get to it, has a multiplicity of 2, which means it bounces. So I'm not going to go through that point. I'm going to come up and touch it, but I'm going to come back down. Now the last point I get to has no multiplicity, so I'm going to go straight through that last point. So we don't know how far down it curves, but it's got to turn at some point. And then we're going to come up through that last point, and we're heading up. And there's your graph. So the last thing I really need to do here is find my turning points. So as I do my turning points, it's where I have a local min or a local max. This is not a local min or local max. It gets flat, but it's still basically going down. So here's your first turning point. There's 1, there's 2, and there's 3. Again, it has to be a local min or a local max, and I have 3 of those, so my turning points is 3. So that is number 8. Moving on, number 9. This one we want to find g of f of -3. So remember what this means. It means this. And what I think we need to remember is that we work from the inside out. We don't just go from left to right. We work from the inside out. I'm finding g of whatever f of -3 equals. So we have to start by figuring out what is f of -3. So that's going to be 1 minus -3 squared. Know your order of operations. We're squaring the -3, so it's 1 minus -3 squared is 9. So 1 minus 9 is -8. So that means I'm going to take g of -8. Again, figure out what f of -3 is first, then plug that in. So this is going to be -8 plus 2 is -6. So again, please make note of how we do those. So that's the composition of functions. That's number 9. Number 10, we're going to identify the domain. Notice this one has just been cut off a little bit. See how that's an open circle? That means we're not including that -3. Also note, it's the x values we're concerned with. Domain is x values, not y values. So this is -3, 0. I'm concerned with that x value. My y value is really irrelevant. Here, my next point is at 1, -4. Again, I'm concerned with that x value. So I'm going from -3 to 1. So your domain, that's what it looks like on the inside. Next, open circle on -3 means we don't touch it. Closed circle on 1 means we do, so we put a bracket on it. That's your domain for number 10. And last one. So this is another type of optimization problem. Again, this is the type you'll see on the exam, so pay attention to this one as I go through it. You can do this one, you can do the one on the exam. So we got a box. It's going to be constructed from a rectangular piece of cardboard with the following dimensions, and then we're going to cut out equal squares at each corner. So here's what this means, and again, it's exactly the same as you'll see on the exam. We're going to take a box, we're going to cut out little corners, so I'm drawing my box right now, Again, we got these little corners we're cutting out. I'll do it a little bit faster here. Okay, so this is what it looks like. Okay, and if you notice, if you fold those sides up, you know you're going to get a box. The dimensions are 20 by 24. So this is the long way. This is your 24 inches, and this is your 20 inches. So what we're doing is we're cutting out equal squares of side x at each corner. So you look at these little corners, these distances right here are going to be x. All of them. They're all the same. Even if my picture doesn't show them the same, they're the same. So we want to find a function that models the volume of that box. So remember, with volume, that is length times width times height. Now we want to take a look here. When we actually make this box, pay attention that the length is going to be this distance right here. Because when you fold those sides up, you got to visualize it, because I can't literally fold these right now, but you fold this side up, you fold this side up, and you fold this side up, and this side up. This little extra space isn't part of your length or your width, because it's all folded up. So this is your length, and your length we want to write in terms of x. We want to write everything in terms of x. So your length was 24 inches, but we've taken away this and this from that 24. So it's now going to be 24 minus 2x. That's your length. Your width, it was 20 inches, but we've taken away, again, 2 x's. So it's going to be 20 minus 2x. So that's going to be your length and your width. So we're going to have length, which is 24 minus 2x. We're going to have your width, which is 20 minus 2x, and your height, which is x. And that is the function to represent the volume of that box. Now if you graph that, again, I'll try to show this to you, but you obviously want to do it. And make sure, again, I'm currently in polar mode. I got to go to function mode. You got to jump back and forth maybe on the test. So here we have 24 minus 2x. I'm going to just type this in. I have 20 minus 2x, and I have x. Now this is going to be a cubic function. And if you graph it, depending on your window, you may have a hard time seeing it. So again, this is like super hard to see, but here's your graph. As you can see here, the x, you got to understand what the x represents. Again, the x represents your height. Now if you're thinking about this picture, x is your height. So if this is 20, your height can't be bigger than your width, or at least half your width, because then I'd have no width. So because you're taking away x from both sides, so the biggest your height's going to get is 10. So if you look at your graph here, if you look at your graph, you'll see at 10, that's where your volume equals 0. So even though it does get bigger afterwards, that number doesn't count because you have no height. You're basically multiplying a negative width and a negative length. That's how you're getting those positive numbers. So in order to solve this, here's what you're going to need to do. You're going to need to find your window. Notice my window in this case is going to go all the way up to about 1,000. So I'm going to type this equation in on my other calculator because I can't calculate on this one. I'll move this back over here so I can see my equation. So you got 24 minus 2x 20 times 20 minus 2x times x. But the window that you have to use on this is 0 to 10. And then we're going to go 0 to 1,000. If you do that, your graph should show, it should almost actually look like a parabola, but as we know it's not. And we're going to find that maximum value. So I'm going to go second calculate maximum, and again it's going to ask you for a left bound and a right bound. So So you find your left and your right bounds, and then we're going to hit enter. So my maximum volume, so my local max, is going to be at about 3.62, and then the volume is about 774.16. Now remember, this is your x value, this is your volume. If you look at the question, it just says what's the largest volume that such a box can have. So the largest volume that's going to be about 774.16, and this was in terms of inches, so cubic inches. It's about as big as you can make that box. You have to have a height of 3.62 to make that happen. So that is your polynomials and functions, and hopefully you're all set.